Good morning, students. In the previous class, we have discussed some important definitions and not properties, advantages, usefulness, and some other introduction about Laplace transform. Today, we will start our class by discussing the more properties of Laplace transformation with some examples. So the property we will start today is nothing but the linear property. What is the statement of this property? If L of ft is fs and L of gt equal to gs, means we have to consider two different functions of t. One is ft and one is gt. Now if you are going to find the L of ft and L of gt, then L of c1 ft plus c2 gt, that is equal to c1 f of s plus c2 z of s. That is, the constant functions, the constants c1 and c2 will become outside to get the Laplace transform of ft as fs and Laplace transform of gt as gs. What is the proof? It's a simple proof. L of ft is fs, L of gt is gs. So clearly L of c1 ft plus c2 gt. Now this c1 ft and c2 gt, which is termed to be suppose ft, then L of ft equal to c1. C1 is a constant coming outside, so L of ft will come. Then c2 is constant outside, so L of gt will come. So clearly c1 L of ft is nothing but fs plus c2 L of gt is nothing but gs. So it's a simple proof. Then we move to the second property, that is the shifting property, which is shortly known as the first translation property also. What this property tells actually, if L of ft is equal to fs, then if as exponential function, that is e to the power at is multiplied with ft, and if you are going to find out the Laplace transform of that function, then that is equals to f of s minus a. Now what is the proof of that? Again, it's a simple proof. For that proof, for the proof of this property, we have to use the definition of Laplace transform. That is L of ft equal to 0 to infinity e to the power minus st ft dt, which is nothing but fs. So here in this problem, or in this statement, we have to replace this ft by e to the power ft. Okay, so 0 to infinity e to the power minus st is same, and now we have to replace this small ft by e to the power at into ft dt. Now if you combine this e to the power minus st into e to the power at to get e to the power minus common s minus a d ft dt. So what will you get here? You have to put s minus a equal to piece of basic transformation, that e to the power L of e to the power at ft equal to 0 to infinity e to the power minus pt, that is s minus is replaced by p, then into ft dt. So it is nothing but 0 to infinity e to the power minus pt ft dt, which is again the alternative definition of Laplace for the function p. That is, therefore this is equal to nothing but f of p. Then that p is replaced by f of s minus a, because already we assume that p is nothing but equal to s minus a. So hence L of ft equal to fs. If L of ft is fs, then L of e to the power at ft equal to f of s minus a. That means when you are going to Laplace transform of a function where exponential function is multiplied, where a is any constant, then whatever should be your fs, that fs should be replaced by f of s minus a. Okay, then so a simple note here. Whenever suppose we are going to evaluate L of e to the power at ft, first we have to evaluate what is the process. That is the procedure actually. What you have to evaluate first? You have to evaluate L of ft first, which is equal to fs, and then evaluate L of e to the power at ft with the help of the first shifting theorem, which will be obtained by simply substituting s minus a in place of a in fs. Okay, that means whatever is your fs, that function s should be replaced by s minus a. Now to understood the shifting theorem, we will have to discuss a simple problem. That is ft, if you are going to find the Laplace transform of ft equal to t to the power 7 by 2 e to the power thrice t. That is e to the power a is equal to 3 and ft is equal to t to the power 7 by 2. So for that, first we have to find L of t to the power 7 by 2. So L of t to the power 7 by 2 by using the gamma function. L of t to the power n equal to factorial n by s to the power n plus 1. So factorial n can be written as n into gamma n. So 7 by 2 into gamma of 7 by 2, then s to the power n plus 1 is 9 by 2. So 7 by 2 into gamma of 7 by 2 can be written as 5 by 2 plus 1 divided by s to the power n minus 2. So gamma n plus 1 is nothing but n into gamma n. So 7 by 2 into 5 by 2 dot gamma of 5 by 2 divided by s to the power n minus 2. Now you just simplify again by replacing 5 by 2 by 3 by 2 plus 1. Again you have to use the gamma function, that is gamma n plus 1 equal to gamma n. So we will minimize this step to 3 by 2 into gamma 3 by 2. Last one more step for breaking that 3 by 2 into half into 1. Again you have to use gamma of n plus 1 is n into factorial gamma of n. So gamma of half already we find out, already it is proved in the previous class that gamma of half equal to root pi. So you just replace that value as root pi, and if you simplify this above terms, 7 by 2 into 5 by 2 into 3 by 2 to half, you will have 105 by 2 to gamma half, root over pi, and 16, 2 into 2 into 2 into 2 is 16 will come out below into s to the power 9 by 2. So this is nothing but that is L of t to the power 7 by 2, that is L of ft. It is L of ft equal to 105 into root pi by 16 s to the power 9 by 2. So the right hand side term is nothing but the function of s. Now actually what we have to find out, we have to find out L of t to the power 7 by 2 into t to the power 3t. Thus we will use the first shifting theorem as L of e to the power 3t into t to the power 7 by 2 equal to whatever should be your fs, that s should be replaced by s minus 6. So fs is here 105 root pi by 16 s to the power 9 by 2. So that s below should be replaced by s minus 6. That is the final result is 105 into root pi by 16 into s minus 8 to the power 9 by 2. Okay, so we will discuss some more problems after ending this ending the Laplace transform unit for the scaling property, the shifting property, the linear property also. Now the next property we will discuss is the change of scale property. That is, what is the statement of this property? If L of ft equal to fs, then L of f at equal to 1 by u. You have to consider one more variable, that is 1 by u into capital F of s by 1 by a into f of s by a. So again the proof is very simple here. For that we have to use the definition of Laplace transform. So L of ft equal to 0 to infinity e to the power minus st ft dt. So L of ft should be replaced by f of at. That is, t should be replaced by at. So in the formula also ft is replaced by f of at dt. Now you have to use some simple transformations that put f at equal to x such that t equal to x by a and dt equal to 1 by a dx. If you put in the original formula, you will have L of f at equal to 0 to infinity e to the power sx by a fx into 1 by a dx. 1 by a is a constant coming outside, so left 1 by a into 0 to infinity e to the power sx by a fx dx. Now again some small substitution is used. Replace s by a by p. Then what you will have, L of f at equal to 1 by a 0 to infinity e to the power minus px fx dx. That 0 to infinity e to the power minus px fx dx is nothing but capital F of small p, because it's a function of p. So 1 by a f of p, that is equal to 1 by a f of p means what? P is s by a. So clearly the theorem is proved. Okay, so now to discuss the change of scale property, we will consider these two problems. For the first problem is we have to find the Laplace transform of cos hyperbolic at, that is L of cos hyperbolic at. So what you have for cos hyperbolic at, cos hyperbolic at is nothing but L of e to the power at plus e to the power minus at by 2. So L of ft, we will move to the definition. L of ft equal to 0 to infinity e to the power minus st into ft dt. So here ft is nothing but e to the power at plus e to the power minus at by 2. So just put it over here. L of e to the power at we already put as 1 by s minus a, and L of e to the power minus at we already put as 1 by s plus a. So if you simplify this term, you will have L of cos hyperbolic at is nothing but s by s square minus s square. So with the similar process, you will have to find, you can easily find the value of L of sin hyperbolic at. Thus the formula for sin hyperbolic at is changed. That is sin hyperbolic at equal to e to the power at minus e to the power minus at by 2. So just replace ft by these things to get the value of L of sin hyperbolic at equal to a by s square minus s square. The third problem is to find suppose L of sin at and L of cos at. So we from the formula e to the power I at equal to cos at plus I sin at. So e to the power I at equal to L of cos at plus I sin at, that is Laplace transform. We use Laplace transform both sides to get L of e to the power I at equal to L of cos at, that can be easily done as 1 by s minus ia, s plus ia by s plus ia. That is a simple formula equal to s plus ia by s square plus s square. So if you use this equation 1 and 2 to get L of e to the power L of cos at plus I sin at equal to s plus ia by s square plus s square equal to s plus s by s square plus s square plus a by s square plus s square. Now equating the corresponding coefficients, we will have L of sin at equal to that is one I is misplaced here. L of sin at equal to a by what is the coefficient of I here, a by s square plus s square, and what is the coefficient of the constant term, that is L of cos at equal to s by s square plus s square. Okay, so these three problems, what we have done in these three problems, we have done the change of scale property here. Moving to the next part, that is nothing but the Laplace transformation of derivatives. So already I told in the last class that Laplace transform can be used for derivatives. So what is the formula for that? If Laplace transform of ft equal to fs, then L of f dash t equal to s fs minus f0. That is for first order derivative. Now the same formula will for the second order derivative, that is L of f double dash t equal to s square fs minus s f0 minus f dash 0. So similarly, if you continue to for the third derivative, that is L of f triple dash t equal to s cube fs minus s square f0 minus s f0 minus f double dash 0. In this way, if you continue this step up to nth step, then what will you have? L of f to the power n ft equal to s to the power n fs, s to the power n minus 1 f0 minus s to the power n minus 2 f dash 0 and dot 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 minus f to the power n minus 1 0. So the proof is actually not required, but for your suggestion, I have just given the proof. But this formula is mainly applicable when we are going to use the application of Laplace transform in solving differential equations. Okay, so generalizing, what finally we will have L of f and t equal to s and fs minus s to the power n minus 1 f0 minus s to the power n minus 2 f dash 0 minus dot 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 f to the power n minus 1 0. So this is nothing but the use of Laplace transform in case of derivatives. So thank you for today's class. next day we will discuss about some more application of Laplace transform. Then we will begin the English class. Thank you.